All right, so with that being said, we're going to work through a quick example here. What's important to note is this is actually no different than if you were doing a regular style displacement question. The only difference is it actually comes out to be easier because we only have to worry about angles for the most part, and we only have to really concern ourselves with whether or not things are positive or counterclockwise or negative clockwise. So we have a centrifuge, which if you've never seen it, is something used to separate out different materials by spinning really fast. But it initially spins at an angular frequency or an angular speed of 12 kilohertz, and it's slowed down at a constant rate until it stops 12 seconds later. And with that, you're asked to find the angular acceleration of the centrifuge. Now, in order to do this, what you want to do is you want to take a look at what you're given and then evaluate what you can find. So first of all, you're told what the angular frequency or angular speed is. Angular frequency is just another name for angular speed. They mean the exact same thing. So what you have here is you have omega, which I'm just going to write as a W because I don't really have Greek editing on this too well. Now, with that being said, we know that it has units of 12 kilohertz or 12,000 radians per second, because hertz just means time or seconds to the -1, and radians don't have any units. But in order for us to process this correctly, we need to figure out what vector angular velocity or angular frequency we have. And that's where the direction comes into play. Here we've been told that we're going around counterclockwise. So I'm going to use standard convention here, and I'm going to indicate a direction with a positive sign. Now, the positive sign here is not necessary. It's not going to change anything. But given that we're using it to identify the direction that this is in, it's nice to actually explicitly write it down. Now, in terms of unit conversions, we can put this in SI units. We can convert kilohertz to hertz, which will give us 12,000 hertz. Or if you really want to, some people like to write this as 12,000 radians per second. But radians have no units, and a division by second literally just means hertz, so we'll leave that. Now, you're also told it slows down and stops at a constant rate over 12 seconds. Now, the 12 seconds is easy enough to interpret. What we're providing, or what you're being provided here with, is a change in time. So here we have the change in time is 12 seconds. Now, with that being said, though, there is a final piece of information here, and it's probably the most difficult one to pick up because it's hidden in words. What you're told here is that it stops. So what this means is your angular speed is going to change. So the one that you started with is of course going to be the initial one. But what you've also been told here is that the final angular frequency or angular velocity or angular speed, you can use all three interchangeably here, is 0. Alright, so again, just like before, pay very careful attention towards like stationary and stopping because they are telling you something rather directly. Now, with that being said, we have these relationships here. The top two are the ones that are used to solve all of our problems. These ones here all convert these angular quantities into tangential quantities around the outside edge of the circle. But given that we just want the angular acceleration, we're not going to need these. And this leaves us with a choice. Now, at the end of the day, we have final angular velocity and initial angular velocity. We don't really know much about how far it has been displaced angularly. So what that means is we're going to want this one at the top because it relates the quantities we're given and it has alpha, the angular acceleration, present in it. So what we can do here is we actually have all our quantities. All we need to do is we need to plug them in. So here, our final angular velocity is 0. Our initial angular velocity is plus 12,000 hertz. And this will be equal to, or this added to this, you will have the angular acceleration alpha and the change in time, which we know to be 12 seconds. So we can rearrange this and solve for alpha. If we do so, what we'll find is alpha here is going to be, first of all, negative, and its value is going to be 1,000. And this will come out to seconds to the negative 2, because hertz is just seconds to the negative 1, and we'll be dividing it by another second. All right, so just for clarity, a hertz is just a second to the negative 1. All right, and this will give us the angular acceleration that we're looking for. Again, some people would like to write this as negative 1,000 radians per second squared, but radians do not have any unit associated with them. Now, in terms of direction, this is actually a rather explicit direction. So we have 1,000 seconds to the negative 2. And if you were looking at this from above, what you would see is this angular acceleration would be clockwise, as indicated by the negative sign that we had previously. And that's typically speaking how you would utilize this. If you were asked for, say, the tangential acceleration, you could just take this thing and multiply it by the radius, and it'll provide you with that quantity.